Audible? Hello. I talked about several of the limitations of present day communications. I mean, places like data acquisitions, not in even many problems that are not really involved in that. So I got started with the first application. Couple of some uh, basic idea of the module is the fact that there is dimension data. The moment you associate a function, which creates a subset and becomes a big number, and the function has dimension data as equate the subset on the function. We are keep doing the subset on the function. Like you find that the function may monotonically exist. So in fact, it doesn't. And there are many cases where even if it's monotonically exist. So there's some interesting broad characteristics. So on one hand, we have these functions called submodular. Have diminishing data means that these are not discrete sets of discrete fields. On the other hand, you have class of functions called the concave function. How do we concave functions behave? What is the typical plot of a concave function? Okay. So some of the function. Imagine that someone right concave. You can explain that. However, concave functions are not easy to minimize. Or minimize. Concave function. Right? But what does it mean to minimize? On the other hand, convex function. Convex function. Could imagine that we should calculate convex function. Now, it turns out that some of the functions, while they were curved, curvature wise, they look like concave functions. In terms of minimization, they behave like convex functions. So the application all around the time. You can also maximize the modular function, but under a budgeted specification, that required So and in fact, there are interesting results about media. So, so what we do is simply deploy the submodularity of the neural function to basically find subsets of given data, unlabeled data, cost, which will always combination. Now, I think I mentioned the last different types of functions. And we have related them to. So, for example, if I am looking for if I'm looking for a subset of these points, 1, 2, 3, 4, 5. Exactly 5 points or 5 images that represent all images. And there's a function that represents I would think of doing some of the similarities or I can max of the similarities to each point. That turns out to be so representation function. And as you would imagine, representation functions will not be these all time. Right? Because you are going to represent X components. One student research and I might not solve a line or sensor based component system. I cannot learn on the way. Because this is one person. That's a problem. On the other hand, diversity function is a very relevant representation in space. Right? Even if the students that's but obviously you can see that you have compromise. Earlier you have picked 1 point for each of these. Now you have picked up 1 point from here and 1 point from here. And then the middle one has been here. Right? This is also determining somewhat diversity based. There are other functions like ability functions. So while representation functions I represent directly coverage functions. For example, I might not look at the bulbs representation points in there. Maybe there's a dog sitting. Dog doesn't eat. It's okay for a dog to eat balance. Spending wants turning on the recognition of is a dog. So that's coverage. You're looking at it. What I so what we also more powerful. Given a query first, ensure that the subset that is selected. very driven substance. Now, very honestly, I would ask people. I may say that I want representative people, or I want people to cover all that possibility. But everything is not for me. Or I might do for private people. Oh, really? It is not working. I want. It is very important now. So you find that car, two cars, but they're diverse cars. There are different forces, color, probably also representing the entire space of cars. Three cars, a big only used to a case. Obviously, this is a red car and only similar to this one. So now, imagine integrating all these with data. That's too much. Problem formulation. Okay, so what set function of in type is type. The general really algorithm which lets you handle all these problems. We talk about data, which is that point or that element which maximizes conditional gain. I include that exactly the effect of what is here. Data algorithms are doing the best. Should stay with you. Unfortunately, for some of them, though they appear right, the greedy strategy, which I think ideally ledger doesn't give you the approval because it is not as nice as most movies are not as nice. But not yet if you get greedy solution as greedy and f of s optimum which you're trying to maximize. They can show that well you can get to 1 minus 1 it can be inequality. Yes. What is this? Greater than equal to less. It will be a at least as good as less than equal to doesn't make any sense. Guarantee as at least as good as 1 minus 1. That's a guarantee. But there are lots of variants for the constraints. So that maximum function is a budget. That's a budget under those constraints. So yeah, since it's also oriented towards the project, obviously we are trying to but we can still use it to visualize all for example, you see that I have put no constraint, no privacy, no query, and it has picked these points in violet. Right? I have put some budget of the budget of 9. It has picked up 10. Put a budget of 10, it has picked up 10 points. But moment I put a query. You see this query in green? Do you see that the selection has changed? What is the selection like here? Yes. How is it? Anyone? How has it changed from the one on the left? This is generic substitution. This query goes. I put one query here, one query here. What's the orientation now? These two have been discarded, right? In favor of a few more points here, right? This point is selected earlier. This point has got selected. So there's a little bit of polarization of the query. Select sector. Imagine I want slightly different polarization. As I said, there are lots of possibilities. So you can do representation, and so on. On the other hand, if I do conditioning based on what I put the red query is a privacy reserved. What has that query did? Now the red this is trust me no, could be around. What has it done? Selected subset has moved away, right? Like repairing all simple optimization problems that can be very useful. So I mentioned last time I rushed to some buildings here. So this, for example, give you effectively of pre-training of large language models. So use something like facility location, take practice examples. No matter what model you're building, model you're building. There's some examples in pre-training. There's something called common growth, not just something even there, which was prepared yes, can do scheduling, can do curriculum. There's a subset that I showed a subset of the partition. It should be more efficient. Got an idea? That leads to some very interesting things. You look at our paper here. Even if you goes to that. If I am looking at drop down or how to now, if you take off-the-shelf model, then you'll find that they're very much biased towards the counting. Why? Because most of the sample images have very low counts. This also the bias coming from physical data. Most images are not. One is not actually now take over the AI case, right? You should take but unfortunately, we can define some of the models in the settings. I think they will not have models that are totally going nuts. Because even if there are 100 people, the crowd model is sometimes 800, 200, is so big. What we said, we can identify partitions. Like a problem. Instead of one type of we have partitions in the data and learn how to models on each partition. Or learn partitions and sensitize your loss function to the partition. If you're within a partition, if you're the crowd comes, what we are, you make an error and because you are on the same bin or the same cluster, same partition. But if the crowd is 100 and it, sorry, or 1,000 and it becomes 2,000, a lot of variation. Now, obviously, a variation of 10 and 30 and a variation of 100 and 10,000 cannot be the same. You are okay maybe with variation of 100 and 10,000, but not okay with variation of 10. So can this partitioning be data acceptable? Instead of fixing a linear limit or a logarithmic limit, can the beginning be data? So we did that. We have to, again, we're not getting into that, but very interesting applications. So we able to do basis of data driven partitioning, and subsequently we also were able to say, okay, can learn the partitioning by partitioning type and learn models for each partition. Use right, so for drop count of 100, the drop count of 1000, first one determine and learn models between and data itself. Can the model data partition exercise happen integrally? You understand? So very interesting. Right? And then I mentioned last time that often you're not in a position even to share data. Also, when you can share data. So it's very important area of federated learning in resource processing where you have local models, let's say one hospital local model, another hospital local model. Subset selection can help very robust. Instead of having to annotate all the data in each of those, you let's say identify a subset that is clear, and you through some federation you are able to learn or share representation. So without getting the map, what I pointed out last time, you can actually learn good separation of the in this case normal exchange versus pneumonia. The green is the normal and so very good separation in a federated setting where the hospitals are not really sharing data with each other, but in some federation the representations are shared. To interrupt your question, but this is just to give a flavor of interesting projects. So you need to start selecting some projects, your research papers soon. I thought I should give you a flavor of the things that we have been doing. Right? We can transfer encoder representation across sites to related representation, but modules of information. Yeah, the other important thing sharing itself. So the second area, again, I would encourage use of all the what I talked about. The fine tuning or the prompt engineering space for large language. I want you to scientific. Think about all. It's not that easy. It cannot be a generic cause. They already use something. So in targeted subset selection, we say that we how do you actually develop solutions of pricing and query driven sometimes. So all of that we borrow from entropy is one of the classical someone nobody studied it that much. But now if you replace entropy, you replace entropy condition with which class of the submodel. You apply conditional gain to H with any of the submodel. You get the gain equivalent of each of those. Okay, so how it will look like. Okay. But what is this? Come with a very generic framework. Say, I want to find subset X of the entire set V, such that the set is similar to Q query and dissimilar from P. And the F itself, the function F itself, can come from any of those classified functions. Now imagine you can have mixtures of those functions. So linear combinations of very interesting properties we use to combine. Given to follow the simple example, motivations, please let me know. Okay, so here are some applications. Imagine I have cameras fitted in many of these security settings, high security settings. It's a neighbor dockyard. Now, obviously, it's becoming very difficult for them to share data with us. How do you realize the impact of AI? So this is what we do. What you can do is, let's say they want to do anomaly detection in lifetime. But it's very difficult for them to create this data set of lifetime and all those behavior. So what happens is typically AI conversation stop. They say ये काम नहीं करता, and we say वो data release, and our conversation stop. Right? So you guys accept this challenge. We can function like this. We can what we do say well, based on this target, you can identify from a large unlabeled set, which is images from their own CCTV. You can pass on our algorithm to them. They use this in a which is and from a large unlabeled set, we identify for them a subset that gives them that if they make okay, we have reduced the task of annotation. On the other hand, we may say, well, there are also large label trading data. Not completely trading data. So people, the security guys, they identify targets. And we pass the all the existing label data. And from those label data sets, we were proper algorithm. Now we have got a labeled small set which is like the targeted setting of the key without even annotating. We see there are so many creative ways. Sometimes you take combinations of these. A combination of the targeted pre-existing label set and combination of their own data set, a subset of the unlabeled data set. All this works very differently. You have Badri and also here. They have done this framework for targeted active learning for document analysis. You have the same situation. Imagine you have optical characterization and a large number of images which are not seen. Now these have very complex layouts. So what you do here is identify a concept of targeted image which you think are the real data, and we able to identify from a very large selection similar images for these. So all this is packaged in that. I last example which I had again. So you may have, for example, the problem of accent recognition in a very underrepresented accent. Again, example of Manipuri accent recognition. And you find that Manipuri accented English cannot able to do English. But what we show is okay. Again, you do targeted you take some targeted accent example, and you have an unlabeled set with all possible accents. You can identify a subset, which is like a Manipuri. It might be actually a mixture of Assamese, Bengali, similar language. Their accents might be similar. But a lot of it may be already this was very I'm trying to, what would you like to do? Should be diagonal or down, right? I want to push down on the off diagonal entries. So let me ask you a question. The off diagonal entries, which entries should be the targeted and which entry should be the frame or the privacy? What would I like to emulate and what I would not like to emulate? Let me ask you a question. We have false positives and false negatives. And on the other hand, you have targeted, and then you have privacy. Which do you think would be suitable for target? Which would be suitable for privacy? False positives means it was meant to be a positive, right? It was meant to be a car, but it's not. Sorry, but false positive means it was meant to be something else, and you got targeted or classified as car. And looking at car, something else has become car. That's false positive. False negative is it was supposed to be a car, it became something else. Right? So what? Let's say I'm looking at a car. What would be false positive? Should it be targeted or should it be terrorism? So it's becoming a car, it is not supposed to be a car. So I want to repair it. Then the other answer is also false negative would be supposed to be a car, it's becoming something else. I want to target. In fact, like this money will be accepted. Again, it's very easy. So yeah, what's interesting is all the production video support. Yes, it's a lot of satisfying experience. Production data based on ML, large scale and of national importance. Also, lots of medical applications. And I was and let's say I have exactly the use case of false positive. If I use these, this actually false positive, then you could also use them as positive. False negative, use them as target. You find that you're doing much better than the So typically these use of false negatives as target is very useful for boosting a tail label accuracy. You can do the same thing in semi-supervised learning. Means I have some labeled data, lots of unlabeled data. I can also learn the unlabeled data. Example, from large unlabeled source, which might classify. But here there's a little bit more about because on the unlabeled data, you don't know the labels. So you have to look at what is the plural labels. Or you have to include the model's performance of the labels. Confidence is on the label as part of the success. So I'm not getting into technical details just to give you an idea. It's another very interesting real has low data regime. Therefore, targeted selection becomes very easy. You want to reduce the criteria of the competition. You want to make sure that you are able to do well on all classes. What they say is finding needle in a haystack. Finding most cancers is like finding a needle in a haystack. Very difficult. But if you show even one more needle, you can probably identify the existing needle more easily. Or very interesting use cases when you have out of distribution. Let's say I have out of distribution. And classic use cases if you have slides coming from a different hospital, there are different kinds of scales, HLE scales. Now, the staining is very different across pathologies. Many things are not as standard as we want. And even it's not just India, it's also there are large challenges that are based on data from the so in distribution could be within the hospital, out of the hospital. Also for different hospitals. So I may have one on the top or actual side. So in distribution would be the same view. But you just change the view. It is not irrelevant, but it's just a different. But you want to make sure that the actual view of one organ is not converted to a second view of the other. So that's why you want to out of and query based on income. This is the other and what they can do is they do household survey. And every house they go and ask for help. They repeat the same question every house. They have audio conversation. Question is standard, questions are repeated, answers are given. And what do they do? They go back and then they sit and hear the audio. What are can you imagine the number of hours they spend doing all this? Doesn't it pain your hearts? And when I looked at it, I was like, shocked. This happens in every state. It's a very complex conversation. Aim and say, right? So we can right? Something. And again, an example of high when you extract something of significance. So I'll talk about the next audio on the side was here. This is again in the spirit of the previous two cold start. And I don't have much data to you. So reduce labeling efforts using data programming in subject. What do we do? Data programming has actually become quite famous because of the effort from Stanford called Snorkel. And what Snorkel does is it lets you write programs and learns parameters on those programs. What do these programs look like? They can be as simple as the speech example, right? They say you can say, well, this is the occurrence of, or this is the text. Let's say I have text, I do text to speech. Anything that matches this template, right? As a rule, should be of type what's your weight. Then I can trigger my what's your weight, try and extract the weight number that comes after this question as a weight. Rules. So rules are ubiquitous and you cannot avoid rules. Right? Even if you have the most sophisticated deep learning. So here's an example. If I'm trying to classify simple example, questions. If text contains how, it's a description question. If the text contains how long, it's a numeric question. If I'm just doing question classification, I can write these patterns. Now, what we say is, well, let's not be naive and just use them as rules. You know that all rules are not of the same quality, right? Which of these two rules you think is more precise? Yes. Which of these two rules is more precise? How long, right? If I have a question, how long, then I know that that's a little bit more precise. So I can put a greater than, which means it's more reliable. So we allow for that. We say we can put quality guides. That's an optimization problem. I'm putting a prior, right? Saying one rule is more black than the rule. Actually, I think a lot of stability to the model. Because what Snorkel does is it treats all rules on equal footing. It didn't have a notion of prior. And as a result, every time we would try to learn models, it was very unstable. Right? So we wrote a paper where we showed, okay, just flip the parameters and the likelihood is still maximized. What a rule which was meant to say, no, cancer, you just associate with not cancer. All flip the association of all the rules and suddenly likelihood is still very high. So sometimes unsupervised learning, because you're learning with no labels, just rules, it is prone to these issues. So you need to bring in some sanity, and again, constraints are very helpful, right? And then, as you can see here, I have very complex example here. I'm trying to give more complex rules. If you're trying to extract relationships, etc. Now, it is not that these rules will operate by themselves. What was the another very important contribution we made? We said these can operate in conjunction with a labeled set. So it's not that you just write rules. You can have them operate with label set. Now these rules can, again, Drew and Buckley, they wrote a whole bunch of rules using signal processing, classical signal processing for images. Let's say you want to do detection of handwriting, right? Find boxes of handwriting. Write rules for extraction from medical records. So rules are not necessarily handwritten, it can be signal processing rules. But yet you may want some very well pre-trained model using some off-the-shelf labeled data set to also operate in conjunction with your rules. That is possible because that's possible because we incorporate several semi-supervised objective functions. So all this is optimization. So there's another example. We have this project Udan, which is actually being extensively used now by education and the State Department. And one of the important points there is that we allow for zero-shot lexically constrained translation. Imagine I have a sentence to be translated. This rule has to be implemented. But if I just give it to Google, is adhikar ko lagu kiya jana chahiye? A rule can be adhikar in some context, but not necessarily here, right? So if I have a domain and I just want to inject dictionaries from the domain and get translation according to the domain, can I do that? Can certainly try ChatGPT, but I'll tell you it's not that easy. So what we said is, well, you build the zero-shot lexical constraint translation. You apply this rule is basically what I was talking about as an example of semi-supervised data programming. It's a program. Saying that is in this domain, these are the possible translations. And it's able to actually pick up the right meaning based on the context. So many other examples. So here's an example of lab reports. So lots of lab reports are still very in hard copy. They're scanned, not digitized. Now suppose I want to extract from these some simple, let's say I want to extract blood pressure. Certain keys and values, name, blood sugar level, pressure, right? So these appear very standard places, isn't it? As an report, one report has it at the left corner, another one has the right corner. Reports may look very standard, even if it's handwritten. The value may be handwritten, the key is often printed. It's a simple observation we made. We can write rules. So here are the programs. Here are a whole bunch of programs. When I write a whole bunch of programs. And this, with a small number of programs, with very less or no label data, we can learn models very effectively. Instead, if you use the label data to actually train a model, use the labeling function, generate label data, train a model, you will actually require a lot more label data to achieve the same amount of accuracy. And there's a negative thing, right? Why can't rules function alongside the models? Now, this is, I mean, there are a whole bunch of algorithms, many from, these are all from our group itself, that we have put together in Sphere. So one big difference between what Snorkel does, again, this is how I think Indian thinking plays a role. You have to think originally. Don't just feel intimidated. Somebody has done something, so we need to copy. So what Snorkel did, it's a multi-billion-dollar company from Stanford. So what they do is they use the so they wrote write their rules. They learn a generative model, and label the data. They learn a generative model, and then label the data and throw away the rules. Once you have generated label data, this is discarded. Rules are discarded. What we have, we call joint approach, which means we don't discard the rules. We have put an and, you can see. For us, the rules and the deep model, they go hand in hand. You don't use the rules just to use and throw, label and throw. Now, there are very interesting optimization problems here. Can you tell me what is the connection between the query preserving, privacy preserving, query focused? How can that be used here? Any thought? So I have written some programs. There's a deep model. They can work together. Do you think rules are sufficient to capture all different types of phenomena in the data? Can I capture every labeling intuition using rules? No. Some of them require the entire context, right? So where do you think I can again use subset selection? Excellent. So let's say I write some rule and the rule has got me a false positive. The rule has injected a false positive. Now, to counter the effect of the rule, to write another rule is going to be maddening, right? But what I can do, I can treat the rule or the outcomes, such outcomes of the rule as privacy preserving. So I can ask the model, here is my rule. There are a bunch of rules I have. Give me other examples to label which are complementary to the rules, which are not covering what the rules have already covered. Right? So imagine posing a problem like this. I want to, you can see this color? No. So maximize function x, function f. Now this x is a subset of the data, entire data, such that the information about or without the rules is maximized. Right? Given what the rules cover, I want to maximize information that the subset carries. So this is the notion of complementing. You want X to complement the rules. Okay. You can apply this privacy preserving subset selection. Is this intuitive? There are other applications where you may say, well, sometimes I can't write rules, but I can say this is an exemplar. Exemplar, like nearest neighbor classifier. How many of you heard of nearest neighbor classifier? Very simplest, right? Find the, or give new query point, find the k nearest neighbor. Assign a class, which is like the max amount, most popular among those k nearest neighbor. Imagine that those nearest neighbors become my rules or exemplars. Obviously, now I have to do some changes to the entire framework. But we found that using those small subset of examples as exemplars is more effective than using them as label data. A small number of labels, label data, we're not able to fine tune the model that effectively. But if you use them as exemplars, they can have more powerful effect on your end model. So this is what we show here. Okay. Yeah. So this is what we do there. We can treat these from different classes as different exemplars. And then again find consensus. The models that I talked about for data programming, you can find consensus we can do. Those consensus in different daily functions. Again, this is using example. Now again, the same thing, same question I'll bring up. Let's say I don't have much label data. What do I do? Well, you are doing targeted subset selection, data ही नहीं मेरे पास, उसका subset निकाल दो, right? They're saying, well, that's exactly where generative AI again sets in. But you don't want to do in the wild generative AI. Right? What we are saying is, and this is something we did become very effective. So, how to select the right images and label them? Can we use generative AI, say replicants? I give an example of replicant, but you can use the diffusion model. That's what some students are working on, the diffusion model. So what we do is, if I give you a target image, I say this is a particular Hodgkin lymphoma. I give that lymphoma, lymph node, and now given a lot number of images, I say generate more images that look like this. This is targeted generation. Or I may say generate an image that looks like my target, but doesn't look like my privacy set. So I can apply the same paradigm, but not subset selection but generation. That's another very large space, a search space. But I mean, in this slide, we just show simple example. If I just do selecting a subset, and then you do data augmentation. This is the clear data augmentation based on the selected subset. Again, the details are brushed under the carpet. Just to give you an idea, if I were to just generate randomly pneumonia and random subset, you will find that all of them are like huddled together here. But if I do informative subset and basically targeted generation, you find that the images are much better spread out. So your generation should have diversity. Again, these are based on TCP plots. So yeah, I'll give you the example how this gets hypertext extraction to speech from medical images and so on. What do I get by spreading out? Okay, so I didn't show in this slide. This is just a diagnosis, but we show that when the images are diverse, and there are lots of papers nowadays on retraining large language models. They show that it's not this large amount of data; it is good, diverse data that matters. Because when you have diverse data, spread out data, then you are building more robust models. Imagine that a model was trained only on this set. It would not know how to deal with, say, images. Let's say there's a query image here. You have no idea how to deal with it. But if the points are spread out, it will be better equipped to deal with, say, an image here. Generate. Generating. These are all possible generation images, but now when I do targeted generation, then I'm much better representing the entire space. Another example where you get data programs become very helpful is when, let's say I'm trying to count cells. You can see this video. I'm just trying to count cells. So cell counting for years, people have been doing it subjectively. We saw that cell counting is a simple program. Number of cells if exceeds a particular threshold, then the trigger. Okay, I'll not get into the details here. This is the whole slide segmentation, right? And we have used this a lot for, as I said, translation. You can see even long translations you can handle using this. I mean, these are actual, completely bank jargon, right? Legal documents, such long sentences. If you just go to give to Google Translate, it's very difficult for it to handle. It's like all over the place. But if you're able to put these phrases, you can find, even for complex phrases, the translation is preserved. This entire area for translation memory, TN. I give a translation memory and I want the output to adhere to that translation memory. So, yeah, data programming. Yeah, so this is the work that Udan has got very effectively. Again, so much you can just. India is basically a very ripe, fertile ground for making AI useful. So this work has been very much appreciated. Used. Several of you are contributing to it. Now, I'll just very quickly talk about other areas where the projects can see. The only challenge I want to tell is so far the other projects don't require too much computation. The remaining two projects I'm going to talk about are very computationally heavy. And if you're going to pick a project in those spaces and come to me, I'm going to really subject you to some acid tests before I give you compute. Better be careful before you choose these areas. They also tend to be a lot more mathematically heavy, but let me run through that. So what is this? This chords, again, is a part of the site. 4 sets of data subset selection. And if you have warm start setting, I give the example of pre-training large language model. It's basically in this space. But how to make models more efficient in the training process. So support vector machines, you've heard of it, right? So what support vector machines do is help you find support vectors, right? Support vectors are, I last class also I talked about support vectors. Right? These are basically support vectors are basically points here. So these would be support vectors, right? Points which are close to the hyperplane, supporting, isn't it? Now imagine that in a deep learning setting, I wanted to find these points. So this entire area is more generally called core sets. Identifying core sets. These are like core sets. You can have core sets, right? Core sets. That's what CORD stands for, core set. In the case of supervised learning, you can have core sets for unsupervised learning or semi-supervised learning as well. You want to train hyperparameters efficiently. Lots of hyperparameters. You can do grid search. But grid search, how what should be the resolution of the grid search? Right? To be more efficient in this space, again, I would like to be doing some kind of core set selection or network architecture search. What network would be the most effective based on validation data? So again, using small subsets of the label data, it's much easier to train models on core sets. Now, core sets are not necessarily just subsets; they are weighted sets. Okay, there's a difference between just subsets and weighted sets. So when I do weighted sets here, or here, I'll assign weights to points. I'll say 0.5, 0.7. So I can have a large number of points, but I'll assign them weights. So again, chords can also be used very effectively. So the chord basically the idea of chord. to identify these points in dark, right? These are the code sets. The code set. Whole bunch of algorithms are implemented there, several of them from our group. Now, I give you a flavor of some problem. You said the right data subset for efficient and robust learning. So it's not just efficient, it's also robust. So here's an example of what we did. One of our initial papers was this one. So let's say I have training data, use a training data set, on which I have a log likelihood function which I want to maximize. So you want to train a machine learning model to find the parameters that maximize the likelihood on the unlabeled data. But you are often interested in using these parameters on the validation data. Right? Training data to estimate the parameters so that it does well on the validation data. So what we did in this paper, we said, well, how about the following? Instead of trying to optimize parameters on the entire training data, find a subset. So let me pictorially depict it. And you may want to kind of draw this. So let's say I have training data U. I have validation data V. Now, the validation data may turn out to be somewhere here. The pink is a training data. The orange is a validation. Is it visible? So what we are trying to say is, I want a subset of my training data such that the performance of the validation data is better. I want a subset of the pink such that my performance on the orange is best. Right? How do I do that? So one simple solution is right optimization. What's optimization problem? I'll say, well, find data which maximizes what? What should I maximize? Some likelihood, some function on the validation data, but over a subset of the training data. I want to maximize finally the so maximize likelihood. I'm just calling it LL. Theta on the validation data. I want to maximize this, but the theta should be obtained on what? The space I want max. But what? How would I connect this to the training data? I'm saying, well, this theta that I obtained should be with respect to the training data. How do I write that? So I'll say I want LL on argmax of theta roughly what am I saying? I'm saying I want the subset of the training data, right, on which I am getting the best accuracy. So with respect to that, I find the theta, right? And this should yield the best performance on the validation data. Okay, so I'm going to write this slightly differently. This is the intention, but since this positive space, I'll write the. It's not here. I haven't written it here, but let me write it slightly more easy to understand now. The overall problem statement is what? Because having an max inside inside the loss function is very scary, right? Can we put it differently? Anyone? So give me the subset of the training data, the pink, such that when I estimate parameters using that subset, my validation likelihood is maximized. Understand the problem? Okay, so how about the following? I'll say max S subset of U max theta. Are you going to help me right now? I'm teasing your understanding. Will this be the right sequence? How will I need the theta to come from the subset of the training data? Theta to be estimated based on the subset of the training data. Whereas the likelihood will be measured on the validation data. Is this the formulation? What would be formulation? Sorry, first. You're saying reverse it? Will this help? What I want is the performance of the validation to be maximized. Remember that. So I want to chase my entire space of training data, all possible power, the entire power set. So my search space on the training data is the power set, right? All possible subsets of the training data, such that it maximizes the validation data performance. So is this going to be the case? But there is the S. How do I get the S? Okay. This does it serve? No, right? Something missing here. What's missing? Where should the arguments be? Inside? Okay. Argmax means that that it maximizes. So S subset of subset of U. So Argmax is S over S. Argmax over theta. S. And then what is this here? S. And then this, right? The entire thing. Say this. This is what I began with some. So you're saying this is entire Argmax. Over what? Argmax over what? S subset of U. Over all subsets of U, find the theta that maximizes for that subset, right? But find that subset for which the theta will be such that the likelihood on the validation set is maximum. So appears quite daunting, right? But I must tell you, this is very practical. Um, when we actually do a couple of things, instead of this objective, we use a first order approximation. So now, why first order approximation is helpful, effective, why it leads to good convergence, this is a lot of theory behind it. We use the first order approximation. That's where we began, and we showed that for certain functions we actually find that the outer objective is submodular or weakly submodular. I'm not getting into any of the math here, but the point is, you want the subset selection to be such that it doesn't consume all the time. पता चला I have applied subset selection, वही time सारा time निकाल रहा हूँ. Right? The subset selection time should be such that it more than compensates for the overall parameter optimization. You should get 10x faster training without compromising accuracy. So we did this, and actually we have several papers on this. Not just this, we also do gradient matching. Instead of just doing the first order approximation, you find a subset whose gradient or sum of gradients matches the gradient on the entire validation set. So you can look at our papers in this space. We applied also this for federated learning. We recently made a paper, and it actually this paper came out of CS769 class project. So this also to give you, good encouragement. Federated learning, you have different clients which don't share data with each other, but we can still do effective subset selection for robust learning. It's not just efficiency; you also need robustness. So, an interesting result in all of these papers is many of these papers is that you get some convergence result, and this convergence result is in terms of dot products of gradients. You can see a dot product here. Dot product of gradient with the training data with dot product with the validation data. This is what gave rise to a whole bunch of other papers they wrote, where we said they not do gradient matching directly. The result itself has convergence analysis itself has a gradient dot product. Why not use the gradients themselves and do gradient matching? So papers we have called grad match. So just to give an efficiency result, right? Almost 3x speed up with no loss in accuracy for supervised SLA supervised learning, and close to 10x speed up for AutoML with AutoML is where you're trying to learn parameters. We had a new paper last year with no accuracy loss. And for robust learning, you want to learn robust model, 5 to 10x speed up. We also use this for there's a paper last year where we use this for speech, a large scale automatic speech recognition. Now here we did something more. We said, well, instead of expecting the subset selection and all the data to be on one server, it's a large number of servers. This is what happens with large language models also. So you want to do partition the gradient matching. So the entire paper, like I talked about gradient matching, right? Is to do partition gradient matching. So gradient matching across partition for efficient and also robust ASR training. So whole bunch of applications. I mean, the hyperparameter tuning, I didn't talk about this. You can all these papers are all going to cover all of these. Let me go to the last module, which is called deep diversified interactive learning. It's again in a warm start setting. I have large amounts of label data, but I want to do active learning in a manner that the model does not restrict. For example, label cost and type and order of management. And this still, we have done some very interesting work here, and I want to open this door for all of you to augment it. For example, this still we have actually brought a lot of data augmentation techniques. Okay, so we show that the effect of data augmentation, which is if I synthetically generate data, flip images, right? Sometimes that compensates for a lot of the annotation exercise. What used to happen until this was out is people would, many researchers would show the effects of or the advantages of labeling, which could be anyways achieved using data augmentation. So we separate out those two effects. We say data augmentation we do and active learning for getting more labeled data. Okay, so this is outline. Again, you do the subset selection here, but this subset selection is mostly for helping identify models, points with respect to the model. So this is not just application of those representation and diversity functions. This is the model specified representation diversity. So you should probably read up our papers, our own papers here. You should feel free to use it. So anyways, all of this have actually resulted in several applications which you probably have seen on our website. But we're coming up with a company called Design for efficient labeling in the biomedical imaging and separate exercises. So that's how much there has been demand for this kind of work. Yeah. And many companies have also made use of it. Now coming to this, what's actually coming up, which I mentioned in the last class, is this entire ecosystem of Bharat GPT and they're setting it now. Udan and other projects I talked about build on Bhashini, which is a very unique exercise with 70 plus academic institutions coming together, contributing data in multiple languages, multiple modalities, right, covering in all the 22 Indian languages. 70 between a technology partner. So what we've been doing is bootstrapping around this success of Bhashini to a private-public partnership. PPP stands for private-public partnership, creating the Bharat system, where we want to release foundation models in all these languages. So we are already in the process of creating those. The idea is this whole lot of companies who are startups in India who need these foundational models, not just the models, they want the recipes. And if you have tried using Llama 2, right, you see how sometimes it's a very steep learning curve. Right? Even in IIT ecosystem, you have people to help. Imagine a startup trying to do the same. So they really need technical recipes. That's another thing we are trying to put out. And therefore, we work with leaders such as NASCOM across all the IT companies. And obviously, this also leads to a lot of curated data set through government applications, a lot of government applications. And going forward, this is going to be important for India's generative AI leadership, all the way to security and cyber defense. Yeah, so there are some important government applications also we're working on, which is for legal, for administrative and public grievances, and also for screening to X-rays and so on. Examples from the legal domain and so on. So, yeah, I just want to impress upon all of you that there's a lot waiting to be explored in the space. So please do very seriously consider data efficiency. Data efficiency is going to be a key to democratization of AI. I'm going just going to take the next 5 minutes to tell you what the next lecture is going to be about. Any questions? So this is, I hope it gets you started with some projects. I gave you enough hints from the last class. And now I've taken you through several applications. I hope you're excited about taking on projects. Seminar reading, the list was out. You should start picking the papers because entire post midterm is going to be largely papers. And projects, I think I have given you a good idea already of at least help that we can provide. We have a community here. You can also pick up other projects, but that could be based on your seminar reading. I would still suggest minimize the use or minimize the dependence of your project on GPUs, specifically A100s. Don't come to me asking for A100s or H100s. Get H100s, even A100s, not possible for last. Any other questions before you get started with your seminar? Yeah, so Design, the Git page has issues. for each of those. So the issues are for each of the different components.
That's the price.
Oh, are you saying, okay, your question is, can the issues themselves a spin-off course projects? That's a good idea. That's a good idea.
Or like, are there other bunch of people could later be integrated?
Absolutely. There are a whole bunch of papers which are also part of seminar, which I would encourage you, data efficiency. For example, direct preference optimization, DPO. It's an optimization problem. Right? Now, can we do targeted DPO? I'll give you the example of targeted. Right? Can we do targeted DPO? Right? Let's say I'm doing, you're doing this RLHF, I'll give you an example. But instead of learning scoring function, I give you the target. Here's and based on the target, I want to do preference optimization on the ground. Very interesting thing to plug in, right? So it will obviously require you to look at benchmarking platforms like they're used for pre-training. Some of them which are also used for prompt engineering. So I think there are a lot of problems around prompt engineering which you can refer directly to this. For sure. Pre-training may see the problem is pre-training algorithms also you can, but to profile them, just to give you an idea, right? While I said the cards paper specifically. These kind of experiments to show that there is a 3x speed up. You need to run the baseline several times. Who's going to give you the computer and the baseline? So basically integrating data efficiency is not difficult, but showing that it works, showing that hyperparameter optimization works. You have to run multiple times without hyperparameter optimization. How are you going to get that much company? Right? And many of these we could do because of collaboration with big companies. That's the reason I feel it's this part is difficult. Pre-training is difficult, but if you're doing anything with the space of prompt engineering, which I showed you last time, there's a whole bunch of prompt engineering possibilities. Bringing in optimization there, I think you can do it. I'm very confident. So I would suggest focusing on that right away. Any other question? So you should start preparing your projects right away. So if you don't have questions, I'm assuming you're all set. Guru, I have updated the slides that there will only be sets of up to size 3. In the next class, I just want to give you an idea of how it's going to pan out. So, sorry. So what we'll do in the next class is continuous optimization. I'm going to take some simple problems. I'll point you to my lecture notes from last lecture, video lecture, because I don't want to get into the mathematical details, right? But I gave you some mathematical problems today from a project perspective. These are much simpler problems, very well-known problems. But I'm going to just show how there is optimization all over. So supervised learning, clustering, principal component analysis, low rank and non-negative matrix factorization, contextual bandwidths, and learning from log data. And then I'll talk about discrete optimization in machine learning. My goal is to be able to complete all of these in 1.5 lectures max. All of these, okay? Because they are just more motivation. But simpler problems, smaller problems to motivate optimization. So 1.5 lectures, I want to complete all of these. So because after that I'll get into the real optimization, some amount of analysis, and then algorithms. Thanks.